Okay, welcome everyone. And I will turn it over to Andrew.
All right, thank you.
You got a couple more minutes, so you probably want to wait until we're officially started at top of the hour.
Okay, sounds good. Yeah, let's wait for people to finish trickling in. Guess I can go ahead and share there.
So I'm going to ask N. Weimer to go ahead and type your name, rename yourself with your real first name and last name, please. And I'd like to also ask everyone to mute if they're not speaking, or if they're not planning on speaking soon. Let's put it that way. Thank you, Nicholas. Yeah, some people default to their username when they come in. Okay, so we're top of the hour. So Andrew, I'd recommend you go ahead.
Okay, thank you. So yeah, thank you everyone for coming to the second half of our breakout session today. As a reminder, here's the session outline. So for the afternoon part, we're going to be hearing from Roberto about just updates on Infix, EXA. Then we're going to hear from Mark about the combustion project. And finally, some combination of Mike and John are going to be giving us an update on AMR Wind. And after that, we're going to have kind of an open-ended discussion. So I'm kind of keeping track of some questions that we might want to talk about during the discussion. But as you're watching these talks, I guess things to keep in mind are, are there any features that were developed for one application that would also be useful in yours? Are there any features that the AMReX developers need to know that we need to know about? And are there any performance issues that you're still seeing that the AMReX developers need to be aware of? So with all that said, let's go ahead and turn it over to Roberto to get to talk about Infix.
Thank you, Andrew. I will share my screen. Hopefully it's going to work. Let's see. Okay, and we'll start. Okay, so hi everyone. My name is Roberto Porcu, and I am a member of the team that develops Infix EXA, which is a solver for chemically reacting multiphase flows in complex geometries. I would first have to say that this project was funded by the United States Department of Energy, NETL, an agency of the United States government, through a support contract. And the reviews and opinions of the authors expressed herein do not necessarily state or reflect those of the United States government or any agency thereof. In the work I'm going to present today, I would like to thank Jordan, William, and Deepak from NETL, and John, Andrew, and Henji from the Lawrence Berkeley National Lab. So to motivate our work, I want to show the data from the United States Environmental Protection Agency that shows how back in 2019, but probably today the situation is so much different. One of the first economic sector for total greenhouse gases emissions in the United States was electricity generation. And in the greenhouse gases, the 80% is constituted mostly by carbon dioxide. So focusing on electricity generation, we can also see that if we we check the data from the United States Energy Information Administration, we see that the major sources for primary energy production in the United States come from fossil fuels, mainly natural gas, crude oil, and so this is energy produced in power plants. So the problem of burning fossil fuels in power plants is that the carbon dioxide produced by the combustion is mixed to many other gases, and that makes it hard to sequestrate carbon dioxide before it gets into the atmosphere. So there are some solutions, and one solution is represented by chemical looping reactors. So in a chemical looping combustion, the carbon dioxide produced by burning fossil fuels in the fuel reactor is mixed only to water vapor. So this makes it much easier and cheaper to sequestrate carbon dioxide before it makes it out in the atmosphere. Chemical looping reactors are being developed. We have an NETL, there is a 50 kilowatt hot flow chemical looping reactor. The problem is that when we scale them up to industrial scale, we don't see the efficiency that was expected. So there is still a need for research and development. And part of the research for chemical looping reactors is represented by numerical simulations. And AMReX wants to play a fundamental role in this sense. So if we go back when we started back in 2017, we were able to simulate a smaller scale chemical looping reactor with cold flow, and a few minutes of simulations were taking a lot of time. And the computational cost was not that big. For example, particle count was about 60 million. But the objective is by 2026 to be able to simulate a few minutes of the real scale industrial chemical looping reactors in a few days on next generation exascale supercomputers. And in this industrial scale, the computational cost will be very high. For example, we imagine to have hundreds of billions of particles to be simulated. These are estimates, but more or less, this is what we expect. So AMReX is a CFD-DM code that solves chemically reacting multi-phase flows in complex geometries. We first solved the fluid phase that is modeled using a particle unresolved multi-component low Mach number formulation. So particles, during the fluid update, particles are kept frozen in their quantities and positions. The complex geometries are modeled through an embedded boundaries approach. For the discretization space, we use the finite volumes method, and we use a Godunov scheme for time integration for the fluid phase. And we solve a system of equations composed by Navier-Stokes momentum equation in convective form, together with conservation equations of mass, species mass, and enthalpy. And we can either simulate an incompressible fluid or an ideal gas, either in open and closed domains. So after we solve the fluid phase, we update the solid phase, aka the particles. We model particles using a soft sphere spring dashpot model. We update in time using a forward Euler scheme with subscaling. So we do several particle time substeps in one larger fluid time step. And we solve a system of equations of conservations for mass, linear and angular momenta, species mass, and enthalpy. And we also compute interface coupling between the fluid and the solid phases through interpolation and deposition operators. We have an interpolator kernel that interpolates fluid quantities to the particle Lagrangian positions. And we have a deposition kernel that deposits particle quantities to the fluid Eulerian grid. And so AMReX is empowered by AMReX, which means that we implement a hybrid parallelism approach. That means we have a multitasking plus multi-threading implementation, where the multi-threading in typically means that we offload the work to the GPUs whenever we can, whenever it's possible. So Amrex GPU strategy focuses on launching GPU kernels into multi-fab iterators and particle iterator loop iterations. This means that in this way, the GPU work is isolated to independent datasets, which can be even further parallelized through using different GPU streams of executions, which give the possibility to use the GPUs at the best, optimizing the GPU usage. Okay, and now I'm going to present some of the improvements that we have implemented in MFIX-Hexa in the past months and years. In particular, in this slide, I'm presenting the improvements we did during last year GPU hackathon, to which we participated. The first change that we did was to pass from an array of struct layout to a struct of arrays layout for particles data storage. These improved greatly the coalescence issues that we had because accessing GPU global memory through storing it, and so accessing and storing it with a layout of struct arrays reduces the problem of coalescence of uncoalesced accesses. And we also improved we reduced the checks that we were doing for particle collisions. So what we do in general for checking particle collisions is that we compute a list of the neighbors given considering given particles. We compute the list of neighbor particles. So that are all those particles that lay within a given distance from the center of the given particle. And we compute collisions. We check for collisions only with the neighbor particles. The neighbor list of particles is updated every a given number of fixed subcycles, but in general, we only check for collisions with the neighbor particles. So this improves, of course, the computational cost because we don't check for collisions with all the particles that we have, but only with the neighbor ones. Something we took advantage of was, and we implemented during the hackathon, was to take the best out of the mutual nature of particle-particle interactions, which means that if the forces coming from the collisions of two particles acting on each particle have the same magnitude but different signs. So theoretically, one particle can update its own forces and the force of the colliding particle. And the colliding particle doesn't need to update, not her forces, not the other forces. So in this way, what we can consider is that, let's say that if we, for every particle was index I larger than another index j, we only put particle I in particle j's neighbor list, while we don't put particle j in particle I neighbor list. And this, of course, reduces the amount of collision checks we have to do. And putting this together gave us a very good performance improvement. We, for example, in this fluidized bed test that we tried, where we have about 3 million particles on one GPU, we observed very good speedups in all the different kernels that update all the different quantities for particles. Where in blue are the old implementation, and in orange is the implementation with the two improvements that we implemented. In the recent months, Henji implemented two very good improvements as well. Actually, three. One is one improvement regards implementation of a greedy algorithm for improving the load balancing with dual grids. So what happens is that the greedy algorithm tries to, for the particle grids, tries to balance particle counts among GPUs and at the same time minimizing the communication between particle and fluid grids. So in this picture, you can see that while we keep the particles local to the fluid grids whenever possible to minimizing the communication between particles and fluid grids, we also try to assign particles to the underloaded GPUs to balance the amount of particles among the GPUs. So this was one of the improvements that Henji implemented. Other two improvements was actually regarding reducing particle communication costs. Henji realized that we were communicating all the particles that were lying inside the ghost regions. Instead, we only need to communicate those particles that are in the ghost regions, but belong to the neighborhood of the particles that are in the destination grid, because we only need those particles to compute particle-particle collisions. So this reduced, of course, drastically the amount of communication that was needed, and also he found out that we were communicating some variables for the particles that are in the ghost regions that were not used for particle-particle interactions. So reducing the number of variables communicated helped as well to improve performance. And indeed, he ran a performance evaluation on a riser with 18 GPUs, and he found out that, for example, you can see that the initial configuration where all the particles, we have only one grid for both particles and fluid, and all the particles are in a few cells. So the particle distribution is very imbalanced. And the baseline simulation was showing a very imbalance in computation, communication, and other costs. And it was taking for sure longer than the optimized simulation that he ran, where all the different optimization were giving good speed up, but the optimization with all the three implementation, the three fixes that Henji did was showing speed up higher than 3. Also Henji's implementation showed to give us much better rescaling analysis on either Summit and Crusher. Here in labeled with 22.02 is the version of AMReX previous to the merging Henji results, Henji implementation in the main development branch of AMReX, and the 22.03 is the one after we merged Henji's changes. And you can see how the results both on Summit and Crusher improved, and we observed also very good scaling results. Now I'm going to present some numerical results for verification and validation of AMReX simulations. In this slide, I'm presenting some results where we try to replicate the simulations done by Jordan in his work from 2015. In the left picture, I'm showing the profile of a particle, a water droplet temperature over time. The water droplet is evaporating in a humidified airstream, while on the right, we have a water vapor condensing on a droplet in a humidified airstream. And in both cases, the profiles, both for the droplet temperature and the energy sources, are in a very good agreement with the results shown by Jordan in his paper, and they're also in good agreement for the condensing case with the experimental data that is that we got from the work by Coolidge in 1976. Another test for verification was run by William. He got the work from Schumann, where Schumann got simulated. Didn't simulate. He found the exact analytical solution for a monodimensional case of a transient heat conduction in packet beds. And the work by Schumann was expanded later by Salehi, and Salehi added in 2017 added a volumetric source for enthalpy for the particles. So what we are seeing here is 4 different configurations. Simulations that William ran with different values for this volumetric enthalpy source. We have a strong source, a weak source, a strong sink, and a weak sink. And in every different configuration, particles are held fixed in their positions, while there is a flux of gas that is hotter than the particles, 30 Kelvin hotter. So you can see how in every different configuration, we got very good agreement between the simulated results and the analytical values. Finally, as a validation test, I want to show the results that William ran. He got the experimental data from Patil of a test that was about a fluidized bed. What Patil did in his work from 2015 was to get experiments of a fluidized bed where the particles were glass beds that were heated up in an oven, and after being heated up at a given temperature, they were immediately put in a fluidized bed where there was a flux of nitrogen that was cooler than the particles, and the flux of gas was cooling down the particles. And so you can see how for a light configuration and a heavier configuration, where light and heavy means the amount of mass for the particles that were simulated, we observed a very good agreement between the experimental data that was provided, provided by Patil in his work, that they obtained this data using infrared imaging, and our simulated values that were temperature of the particles averaged in the entire domain. And we observed very good results as well in this case, for this case as well. So yeah, thank you for your attention, and I'm available to questions if anyone has questions.
All right, thank you, Roberto.
Yes, I have to stop sharing my screen.
Well, you can keep it up in case someone need to refer to some slides. Does anyone have any questions for Roberto?
A quick one, maybe. Near the beginning, you talked about cutting the search in half by understanding that if you found particle I to interact with J, then you'd have to do the reverse.
Yes.
Is that a capability that's now part of AMReX search? Like there's an extra special kind of search to say that that's what you want, or did you do something special with the return of the search?
Yeah, that's a good question. When we use the AMReX neighbor particle container, and the neighbor particle container, when we compute the neighbor list, we pass a function that computes the neighbors depending on whatever you want, right? So it's a class where that has a operator that returns whether a particle should be or not in the neighbor list, right? So for example, if a particle is below, the distance of a particle is below a given distance from the center of the other particle, then that particle is in the neighbor or not, right? So that's the discriminant. In the same operation, we can also check if the particle that is supposed to be in the neighbor list index is smaller than the particle I index. So in that case, we put that particle in the neighbor, otherwise we don't. So what happens is that with this check, one particle is going to be in the other one neighbor list, but not the opposite. And so it's something that we did in Amrx, but it's very easy to implement because it's Amrex makes it very easy to do it. The particle container that Andrew implemented makes it very easy to do that. And then you have to take care, of course, when you update the quantities when we do the update in Amrx, we have to be very careful because this particle is going to update her own forces and someone else particle forces. But this could be also true for another particle, right? To update this particle forces. So we have to do atomic operations, which of course is the bad part. You don't have free lunches, right? Is the bad counter effect of side effect of this, but it proved to be more efficient to have this halved neighbor list and using atomic operations instead of having a full neighbor list, and not using atomic operations.
Excellent, thank you. That's great.
You're welcome. You're welcome.
Cool. Yeah, any further questions for Roberto? All right, if not, next up is you, Mark.
Also, you're muted.
Yeah, I think you're muted, Mark.
I can't be.
Oh, there you go.
Okay. Now I have to go once a week and be told that I'm muted. I think we all do that, but maybe I get a little bit more. Thank you. So, yes, I was asked to give kind of a summary of the Pele project, and I was left a little bit to interpretation. I knew that there'd be a fair number of people in the audience that already knew a lot about the application. So I was a little unclear about what to talk about. We'll see how it goes. First thing is the Pele team is getting to be a pretty large group. Some of these folks worked on the Pele project for just a year or two in the past, and some are just starting up. I don't think that represents how many FTEs are in the project, but just how many people had their fingers in the pie here. Pele Combustion Suite. So Pele is Exascale's application suite for high fidelity detailed simulations of turbulent combustion, both in open and in confined domains. The idea was we wanted to create a numerical capability that included enough detailed physics and geometrical flexibility to be able to evaluate the design and operational characteristics of a number of different types of combustion devices for automotive when we first started, but now expanding into industrial and aviation applications. So in order to do that, we had to target kind of a range of simulation capabilities, which I'll go over by visual aid with the picture on the right. But we're trying to include enough physics to be able to inform the next generation combustion technology design. And just some examples of the sorts of devices we're looking at. The first one is the RCCI, which is reactivity controlled compression ignition engine, which is part of our KPP2 challenge problem for the ECP project. But also we're interested in things such as supercritical CO2 power cycles, interesting looking rotating detonation engines, supersonic cavity flame holders, and again, more recently looking at aviation combustors for looking at sustainable aviation fuels. Focusing a bit on the picture on the upper right, this kind of describes our KPP2 challenge problem. So as a KPP2 project, we formally came into ECP without this capability. And so our goal is to demonstrate a useful calculation that fills up the machine. So definition of useful here is somewhat subjective. What we decided to do was look at a spray fueled or jet fueled piston cylinder. This is a cross section of a mostly cylindrical cylinder with a funny shaped piston head that's dark gray. You got jets coming out of the ceiling and headed towards the piston bowl surface. Hopefully it'll form a turbulent diffusion jet and will burn stuff before it gets to the wall. And we want to be able to do this with enough fidelity that we could understand the effects of, let's say, fuel composition or timing of the sprays and things like that. And in order to do that, we have to be able to capture some critical physical processes like turbulence, mixing, spray vaporization, low temperature ignition, which is kind of a special property of the sorts of fuel that we're looking at, flame propagation, and soot and radiation. So to do this, we constructed something called the Pele Suite, which consists of several PDE solvers working in different flow regimes, which I'll describe coming up. Something called Pele Physics, which provides the databases for the thermodynamics, the transport properties, the finite rate chemistry models and such. Something we call Pele Analysis, which provides a bunch of tools that are specific to two things, really. The first is adaptive mesh refinement, so block structured AMR. And then the second is understanding this kind of high dimensional composition space. So, you know, kind of specific to combustion problems. Pele MP for multi-physics is sort of an add-on to all of the integration codes. to add a soot modeling capability, radiation modeling capability, and the ability to incorporate multi-phase models in the form of Lagrangian particles that evaporate and fuel the domain volumetrically. And then Pele production is kind of where we keep all of our runs and pass them around amongst us. So the code is structured kind of generically as a picture on the lower right, where AMReX kind of underlies most of the code. Sitting on top of that is AMReX Hydro, which manages a lot of the details of the hydrodynamics and its interaction with the geometry. Pele Physics I've already touched upon. And then the column on the right is our interaction with third-party libraries. Most importantly, I think at the top is sundials. We depend on sundials to provide a range of integrators to deal with our chemical kinetics. And we could either use implicit or explicit in time integration processes. But without sundials, I think we'd be sort of dead in the water. Supporting sundials is Magma, which is a batch linear solver. So point-wise, you have to solve nonlinear systems if you're integrating time implicitly, and Magma helps us invert some of the matrices that are associated with that. Hyper, on the other hand, is a distributed linear solver, which we'll use primarily for the projection operator and the implicit diffusion, which I'll talk about shortly. So looking at the integrator codes, the simplest of the three is Pele Suite. That's a compressible flow solver for conservation of species mass densities, momentum, and total energy. It's based on a time explicit Runge-Kutta based variant for diffusion and hyperbolic terms, and that's coupled with the sundials driven ODE integration for finite rate chemical kinetics. And depending on the regime that we're looking at, we might want to do an implicit or an explicit integration. And in fact, depending on the machine we're operating on as well, depends on a lot of factors. We're still trying to quantify which ones are most efficient and which combinations of stuff underneath. I'll talk maybe a little bit more about that in a minute. So again, Pele Physics will then supply to Pele C everything it needs to actually evaluate the physics models, including the transport coefficients, the equations of state, all that fun stuff. And then you can wrap over the top of this Pele MP, which you can use to push particles through the system, and then they might react. Pele LM and Pele LMX, they're written like that because they're both very similar codes. LMX was derived from LM, but they're different in a key way. But both of them solve the low Mach number flow equations for conservation of mass densities, momentum, and enthalpy. The larger time steps that are enabled by a low Mach number approximation requires that you pay a bit more attention to the coupling between the diffusion and the reactions, essentially. So we've devised this iterative implicit spectral deferred corrections variant of a time stepper. We couple these things together nicely when we take big time steps. Time steps are big enough that we can't do explicit diffusion anymore, so we do a Crank-Nicholson-like step. And then the hyperbolics are based on BDS, Godunov stuff, and I'll make a comment about what BDS stands for and what its purpose is in just a minute. The chemistry is again driven through Pele Physics, using sundials to integrate the equations. More often than not, the time steps are big enough that we have to do an implicit scheme in order to get the chemistry to solve in my lifetime. You end up taking hundreds of thousands of time steps. If you have to do it explicitly, that'd be bad. The critical aspect with Pele LMX, and the reason why, in fact, there's two lines of development here, a low Mach and a compressible version of these codes, is that in order to integrate the low Mach number system, we have to solve a linear elliptic system in order to get the projected or constrained velocity field that satisfies a spatially constant pressure field. We also have to solve a set of linear systems to do the implicit diffusion solve. So Pele LMX turns out to be a lot more complicated than the compressible version because it involves the necessity of solving these linear systems. Moreover, things got worse when we started adding geometry for reasons that we don't fully understand yet. The more complicated the geometry, the more sensitive the linear system is to details about exactly how the geometry hits the grid and other things that we don't fully understand. But what we do know is that for a range of cases that we're looking at routinely, during our ECP project, we find that the linear system associated with that elliptic problem can be horribly ill-conditioned or not, depending on whether you wiggle the geometry with respect to the grids. There's a lot of interesting things happening numerically when we form these linear elliptic systems in these embedded boundary cases. What that meant was we both need to understand what's going on, but in the short term, we still need to solve the problem. So we spent a fair amount of time working with the hyper folks to robustify the algebraic multi-grid solvers that they have, because the multi-level multi-grid solver that comes with AMReX just doesn't do very well in these very ill-conditioned cases. So I'll try to make a comment about specifically what I mean by these iterative solvers. Near the end, it might be coded so that not many people understand it, but it's brilliant work, so I should at least mention it. So the primary difference between LMX and LM is encased in that last bolded bullet point. But LMX is just like LM, except that it does a non-subcycle time stepper, which means that we take the same time steps in the algorithm on the coarse grids as we do on the fine grid. And for technical reasons, which I'm not going to go into, what that is allowing us to do is to do AMR in a closed chamber, like our KPP2 challenge problem is, and like a lot of problems of interest are, where in a closed chamber, when you have heat release, things going on, you have fueling, the system pressurizes. And it turns out that it's a little tricky to manage a pressure, even though it's constant over space, to manage in a time-dependent pressure, and also do that.
J'écoute un truc. J'avais oublié que Marc.
Well, someone needs to be muted. That was a question I didn't understand. Let's see here. I didn't make it. Oh, I didn't show the movies. Gosh darn it. So while I'm talking, that movie playing now is to maybe try to give you a sense that we're getting very close to being able to run this KPP2 challenge problem. We could run problems where we're injecting sprays into a closed domain with a funny shaped piston head. The jets are going into these things and they're mixing, doing some nice turbulent mixing. And so we have a lot of the components in place. And now it really is about scaling the system up, robustifying the linear solvers, and getting all the pieces to hang together. So those are the three main codes. I'll give you a couple more comments about Pele Physics, which talks to all three of them. Pele Physics is itself an open source combustion physics library. It has all the junk in there necessary to get the behavior of the gas system from the equation of state. The equation of state might be an ideal gas mixture. It might be a non-ideal one for looking at supercritical flows. It might even be EOS lookup tables. Pele Physics supports them all, and the codes that use it support them all. Transport coefficients can be mixture averaged, which is typically the model that we use. We're interested in, let's say hydrogen diffusing faster than some heavy species. That makes a difference in how our flames propagate. We want to be able to capture that. But then there are simplified models like a unity Lewis number transport property where there's no variation over space. So there's various simplifications. And then finally, the chemical reactions themselves, finite rate chemical expressions, are typically specified in the combustion community using this Chimkin formalism. And we have a Python code generator that spits out code that builds on CPUs or GPUs for efficient evaluation of those, including the ability to handle things like what's called a quasi-steady state assumption, where some of the species, instead of satisfying ODE expressions, they'll satisfy algebraic expressions that say that their creation rate is equal to their destruction rate. And so the value of a concentration of one of those kinds of species becomes an algebraic relationship that you carry through the evaluation of the rate term. So it's a nice way to reduce the dimensionality of the system by making some approximations to the chemistry. I made reference to lookup tables and sort of other ways to evaluate equations of state and chemical reactions and such. And here's a picture of why one might want to do such a thing. It happens that in many chemical systems, They might be very high dimension, they might involve hundreds of chemical species, but when you look at the dynamics of the system, it turns out that you can pretty accurately describe the dynamics with a much lower dimensional chemical space. And the coordinates of those chemical spaces are often some linear combination of the normal variables you would use. And instead of evaluating very complex finite rate chemical reactions, you can store the relationship between the bases in this reduced manifold space and the effective production rates. You can store that in a neural net. And so the use case here would be you do some very complicated, expensive simulation, but you keep track of the data that was involved. You could store the chemical space that was accessed during those runs in the form of a very reduced neural net. And you can replay those calculations with maybe different boundary conditions. As long as you don't go too far away from where you did the original calculation, you can redo these calculations in a much, much lower dimensional space, 2 or 3 dimensions rather than say 100 dimensions. So there's good advantages to that. And this is going to become useful, post ECP, when we have to do a lot of engineering calculations in, parts of domain of parameter space that are fairly limited, but we need to do a whole bunch of iterations to do optimization and things like that. Anyway, back to the code. The numerical methods used in Pele are similar to a lot of other AMReX applications. We extensively leverage the AMReX library, including the data structures, the communication patterns and tools, the description of how parallelism is handled, and in particular how the GPUs are accessed. All of our discretizations are based on cross-refinement finite volume methods to conserve mass and energy. We talked about the subcycling, Pele C and Pele LM subcycle in time to maintain typically a constant CFL across the AMR hierarchy, whereas Pele LMX tends to run with a single time step across the hierarchy. They have different advantages to the algorithm, namely their ability, the low Mach number code's ability to handle closed chambers. I mentioned in passing earlier that the Pele analysis suite contains some tools. Here's some examples of what they are. They're typically AMR aware, so they understand how the grids are nested. They understand the high dimensional space. They provide tools to extract isosurfaces, slices, streamlines, stream tubes, to be able to incorporate high dimensional sampling and statistics, to do some analysis in the chemical space, including CEMA, which is chemical explosive mode analysis. You're looking for positive and negative eigenvalues to the reaction Jacobian, or reaction path analysis. You're understanding how carbon in the fuel is finding its way to carbon in the products, things like that. Also, the development of these reduced order models, the machine learning training, all those kinds of things are all supported in this analysis, and as well as providing support for in situ and post-processing stuff. I made reference to the geometries being incorporated with AMRX's embedded boundary stuff. In general, AMRX provides functionality for arbitrary domain boundaries, internal and external, in 2 and 3D, providing some tools to generate these things, some simple shapes, more recently, some computational solid geometry, ways to pull things out of CAD packages and create geometries from that, or create surface meshes and use that to create AMRX's description of the geometry. Those last 2 things are in development, in testing, and eventually will be a critical part to us being able to apply this post-ECP to more complex general situations. But other than the generation, you have the data structures, augmentations to the logically rectangular stuff that normally comes with block structured AMR, but the augmentations allow you access to things like the apertures of the faces, how much is exposed to the fluid versus how much is covered, and also abilities to create numerical PDE operators like gradient and divergence and such. This is all kind of standard AMRX stuff. And in these cases, what happens is, as shown by the picture, as mentioned in earlier talks, the regular cells are cut or completely covered by the EB, and the corresponding stencils have to be locally modified near that boundary to account for partial obstruction of the faces, partial obstruction of the volumes. Redistribution turns out to be a really important aspect of this because those cut or small cells will have an instability for time explicit integration of things. When you're trying to time step at a DT that was based on a CFL constraint that was based on the full cell. So if you get little tiny cells, you're going to have instabilities, and redistribution is a way to manage that. So I'll make a couple of comments about that. Again, redistribution is used to robustify the conservative update. So what you do is you involve the small cell and a couple of its neighbors. So you end up getting kind of a bigger area to work with. It has a way of helping you get around the instabilities, but it also involves a bit of arc. So you have to decide when you do this redistribution, which cells do you want to involve in such a procedure, and how do you want to weight the redistribution of mass or energy to do this. AMR provides a number of different methods they have over the years. I think they're narrowing down, but specifically for the combustion application for complex reacting flows, we find that we're evolving mass fractions, and we need those mass fractions to stay between 0 and 1 during evolution, or we're in trouble. So sometimes if you're doing kind of a gamma log gas or some idealized system, maybe you have overshoots and undershoots, maybe you can just clean them up. But in the combustion problem, we have to evaluate transport coefficients, thermodynamic properties, chemical rate expressions. We can't do that. In addition, the flux interpolation and limiters and some of the other things down in the bowels of the AMRX's redistribution schemes could introduce or compound these bounds violations, and that would just essentially make our code crash. So the Pele team has worked extensively with AMRX to develop and test redistribution schemes that preserve these constraints. So it's important to fix those at boundaries. It's also important when you're doing God and off, you can have overshoots and undershoots. So with extreme gratitude, we appreciate the efforts of Eric Palmer and Andy Nanaka to bring in the Beldas and Shubin advection scheme, which is a nice multi-dimensional way to do upwinding that really does a nice job preserving this positivity. So at least in the low Mach number case where that scheme is appropriate, we can now get back to taking time steps that are, CFL size time steps. We can avoid generating overshoots and undershoots within the domain due to regular Godunov stuff that you would normally see, and at the embedded boundary due to the redistribution stuff. So a lot of the work over the last year has been to address this issue and make sure that we can have a nice, robust evolution of our state, no matter how complex the geometry. I don't want to say much about moving the Amrex codes to CUDA and to GPUs, except to say that in Pele, we spent actually a fair amount of effort investigating a number of different approaches to doing this, involving things like OpenMP and other strategies of mixed language implementations, trying to minimize as much work as we had to do. Ultimately, for a number of reasons listed there, it turned out going the AMRX's lambda-based lambda-based approach to launching kernels turned out to be the most efficient, turned out to be the most easily readable and maintainable code, and it let us get rid of the multi-language implementation and go to an all C++ framework like most of the other ECP applications of AMRX. So it's turned out to be a big win for us. Now, let me see where I'm at here to probably get really close to time. We just want to make some comments about the current status of the scaling. We're now running Pele C and Pele LM across all of Summit and on all the pre-exascale machines. Everything builds, runs nicely. The weak scaling plot there on the left shows some degradation in performance as you go out to a very large number of nodes. But what it also showed us was when we grind through the numbers, that scaling is sufficient for us to meet our KPP. So on one hand, we can work to improve that fall off and look at, and I'll show you in the next picture what's causing that. On the other hand, it's not the highest priority because we can actually meet our goals for this project with that kind of scaling. Strong scaling, I put the plots up there. To be honest, I never quite know what to make of it because we're not particularly interested in the strong scaling limit of these codes. We're looking at filling up Frontier with a big calculation. So that's, again, something we'll have to work on in the future. For Pele LMX and LM, the story is very similar. We have a fall off in the weak scaling, but that fall off when we grind through the numbers turns out to look pretty appealing for us and being able to meet our KPP goals. So I think we've shown that we're in just fine condition to meet our KPP goals. In fact, we have the compressible code running right now on Summit to generate our initial conditions that we're going to use to launch our Frontier run for KPP2. We hope to have LMX running the same calculation, both for verification of the Pele C result, but also so we could demonstrate that the more complex code is able to meet the same criteria. As promised, here's now getting to be a little bit old of a plot on the left, which shows that as you crank up on Summit to over 4,000 nodes, most of the key routines in our advance for Pele C remain pretty much the same in terms of relative amount of wall clock time spent in those routines, but there's one nasty one there, the third one, the parallel copy finish routine, which doesn't scale well. And that turns out to be the reason we believe that we're losing our weak scaling. But again, it's not killing us on the project. It's just something that needs to be fixed. Both codes have similar performance stories. So if I looked at LMX, it would show a very similar scaling issue with node counts, but we're also seeing that on single node calculations, we are getting what we would call performance parity between Summit and Crusher. Means that when you factor in the number of GPUs available per node, we're getting essentially the same performance on Summit as we get on Crusher. So I think this all means good stuff. I won't bother trying to explain this. I'll leave it in the slides and you can look at it later. It essentially says that we found a really robust, beautiful way to solve incredibly difficult linear algebra problems. All that stuff's being backported and accessible to be made accessible by hyper users. And we intend to use that, and we're going to need to use that when we solve progressively more complicated problems. But it's essentially proof that we're going to be able to pull off the low Mach numbers calculations along with the compressible calculations to meet our goals. That is the end of what I wanted to present. Very light on technical results, but just sort of giving a layout of what Pele is and where we're at with things. So happy to take any questions.
All right, thank you, Mark. Yeah, any questions for Mark right now? I was a little bit curious. So how do you model the soot? Is that like a second fluid with like a different equation of state, or?
Essentially, it's a moment model. So there's soot really is a distribution of carbons, and so you keep track of the size of the soot particles in different moments, and then there's an interaction, an exchange between moments as you create smaller particles or small particles coalesce to large particles. It becomes a source term between the two as they talk to each other. So it's a very simple model. There is actually, much like radiation, there are a huge variety of techniques that have varying levels of detail and expense associated with it. But it turns out to model it in these combustion scenarios, you don't really need a whole lot of detail.
Okay, thank you.
This is Jackie. Can I ask a stupid question? Maybe since Ann and John are also on the line. As a user, one of the things, we love having embedded boundary and cut cell because we can do complex geometry, but we're always dealing with turbulent flows, and therefore you've got turbulent boundary layers and near wall physics going on. So is there any way to have have rectangular blocks instead of square blocks near walls or cut cell regions so that we could have finer meshes in the wall normal direction and resolve information, close to the boundary layer, inside of the boundary layers better?
So I could put a spin on your question, or I can just shut up and let Ann answer it.
Yeah, I'm putting all you guys on the spot.
So Jackie, this is Anna. I guess the question is, what do you mean by is it possible? So can you have dx not equal to dy not equal to dz? Absolutely. Right. AMRex has no problem with that.
Okay.
So the question is in your and in your algorithm, the way it's written on the Pele side, it may or may not assume that those are square. You are going to see, though, you're going to have consequences in your linear solvers, for example. So yes, you can, but it will have consequences like your linear solvers are going to perform optimally when the mesh spacing is equal.
Mm-hmm.
So yes, but it may not do what you want.
Okay, is there any other workaround? I mean, right now, the only workaround is to do an implicit LES near walls, or we have to put a near wall model in there.
So it's worth remarking also, this is John,
Hi, John.
that in another project, it hasn't been pulled back into AMRex yet, but
Yeah.
they are developing a curvilinear type capability that would allow you to locally stretch to have smaller grid cells near a boundary.
Mm-hmm.
And again, as Ann said, you'll have to go to an algebraic multigrid to be able to do the linear solvers, but maybe that's not such a problem.
Okay. Well, maybe we should closely follow what you guys are doing there, because yeah, this is going to come back every time, right? We've got half the problem solved with the geometry, but then the other half is resolving the gas flow near the surfaces.
Right.
Right.
That's whenever you're deciding how you're going to handle complex geometry, one of your questions is, do you have boundary layers you need to resolve precisely for this reason? And so the way that the ExaWind project manages that is to do, overlapping grids to where they can fine tune the shape of the grid and discretization near the boundary, because that turns out to be very important for their problem. That unfortunately, as you'll see, introduces a lot of complexity in software. Yes, there's as many approaches to handling this particular problem as you want to try to throw at it. And it's the question of how important is it to the application space that you're interested in? Is it worth bringing in that level of complexity?
Well, if it's working and proven technology in a different domain, maybe it's worth porting, but not until that it's let someone else work out all the problems.
Yeah, that's definitely an advantage to working with AMRex as an underlying framework, that we often get the benefits of a lot of these different applications almost for free, relatively speaking.
Right.
As improvements are made or capabilities are added. So that's always a possibility. But I suspect that this particular topic is going to be less for free than many of the other things that we get from AMRex.
Thanks.
All right, anything else for right now? If not, let's hear the final presentation, which will be about the Amr Win project.
All right, let me try this share. Is that showing up okay?
Yep, looks good.
Let's see. Okay. So thanks for inviting me. I'm going to give a talk about Amr Wind, mostly about what is Amr Wind, and then our hybrid solver work that we do, and give some updates over the past year. So I'm going to give this talk, and then also John Rood is going to talk about a few slides, maybe 2/3 of the way through. And I didn't list the ExaWind team. It's a lot of people, but a lot of this work, I'd like to mention at least Ashesh Sharma. He did a lot of this work. It's really good stuff. And I think both the PIs are here too, so Mike Sprague and Paul Crozier. Okay, so the ExaWind project really has two parts. So there's the ECP part, which we're all familiar with. Our challenge problem is to simulate 4 blade resolved wind turbines. approximately 20 billion degrees of freedom inside of an atmospheric boundary layer on an exascale machine. So that's kind of a problem statement. And then we also have this other project called high fidelity modeling. And this is where a lot of the onshore and offshore work for wind turbines happens, all the physics development and the verification and validation. So both these projects work really well together. ECP, working on time per time step and scaling, and HFM adding all the complicated physics to pull this off. All right, so what is AMR Wind? So AMR Wind was forked from InkFlow in spring 2020. And it's very similar to IAMR. So these are all AMRex codes. And they rely on the block structured AMR that's in AMRex, the performance portability that gives us, and also MLMG. Because we solve incompressible Navier-Stokes, we have linear solvers are very important to us. So having a scalable, robust solver is good for us. So after we forked it, we started adding stuff to it to make it different. So one of the first things was atmospheric boundary layer physics. So these are things like Coriolis term and Boussinesq buoyancy and wall models, stuff like that. And then we've also added actuator lines, multi-phase flow, immersed boundary method, and then I'll talk about this hybrid solver. So where we combine AMR Wind with Nalu Wind through Oversight using Tioga. Right, so the AMR Wind discretization, most of this comes from this 1998 paper from Anne Almgren, a JCP paper. So it's an approximate projection scheme. The velocity and scalars are all cell-based and pressure is node-based, and it's also staggered in time pressure. Discretized using a finite volume method and a Godunov scheme for advection. We also have a WeKnow-Z variant that we typically use. And because we're solving incompressible Navier-Stokes, we rely on these three types of linear solvers. So we've got the MAC projection, Helmholtz solves for momentum and scalar. And those are both 7-point stencils. And then we also have a nodal projection. It's a 27-point stencil. These all come through the AMRex library. So in addition to incompressible Navier-Stokes, we also can solve large eddy simulations. So that's either through the Spagrinsky model or you can add an additional equation and use KSGS. Here's just some velocity and temperature profiles of a neutral ABL. So this comes from the Peterson paper. He labeled it N02. But you can just see if you take one of these atmospheric boundary layers, they're periodic in the XY. You simulate it for a while and then the flow develops. And then these plots are made by both spatially averaging the whole plane in the XY, and then you do like an hour of physical time on time averaging just to kind of smooth it out. So you can see you get your typical boundary layer that forms. And then this is called the neutral ABL, which pretty much means that temperature doesn't affect the simulation. So you can see the temperature profile is flat in the lower part of the domain. And then we put an inversion layer in, which kind of just acts like a lid to this problem. So we're really just mostly concerned about what happens in the lower portion. And so what's nice about this case is we compare AMR Wind to Nalu Wind to SOFA and to that Peterson paper. And so we have pretty decent agreement. These cases are kind of hard to get good agreement just because they're a large eddy simulation. Here's a different case that we work on a lot. So it's called Gables. There's a great website. I put it here. It has all kinds of data from tons of codes. It's really good to compare to other codes. This is kind of similar, except that for this case, you start with a temperature profile that varies linearly, and then you cool the ground as the simulation goes on. So you can see that there's temperature has an effect on the simulation, and that is partially related, causes this nose to happen. So you can see, maybe 150 meters up, you can see this nose. So the flow goes faster than the free stream flow that we started at. So that's kind of interesting. We also recently have some multi-phase work, so it added some movies. Movies are always good. So here's a dam break problem. A lot of this work's been done by Yorgos and Michael on the Excellent team. So this multi-phase work is going to be important later when we start doing offshore wind energy. Couple everything together. Oop. All right, I'll quickly talk about some strong scaling. This plot's kind of old at this point, but I still like it because it has 2 problem sizes and it has GPUs and CPUs on Summit. So you could see how if you do a lot of degrees of freedom per GPU, you get really good speed up compared to CPUs. But when you strong scale them all out, we're still a little bit faster using CPUs. There's just not enough work on each GPU. And then this is a fairly big problem out here too. So that's kind of nice to see strong scaling is looking okay. Here's an improvement over the last year. So I just went back in a year from April. So this is new is this past April, and then old is April 2021. And I changed 3 things. So it's kind of hard to say, which had the biggest impact, but of course I updated AMReX in that year. We also realized with the collaboration with Seed that, so they were doing this, a different solver for their momentum solves. And they said that we should try it. And it turns out it works pretty well. So we run such a small time step because we're trying to do large eddy simulation that using MLMG, like a whole V cycle just is overkill for those. So we've switched to Krylov solvers and we just set the max coursing level to 0. And that's led to some speed ups. And then also we've gone from a tensor solve to a multi-component solve. And that was just a little tiny speed up. But all 3 of those things gave us 1.3x speed up. So that's pretty nice. All right, so now I'll talk about the hybrid solver. So this hybrid solver, what we mean by that is that we're just connecting multiple codes through Oversight. So you can see this picture here. We've got a background grid. So sometimes I'll call that the off body. And then we've got the near body grid. That could be stretched and it could be unstructured. And so typically we'll put Nalu Wind, which is our unstructured code there, and then we'll put Amr Wind on the off body. And so the reason we use Oversight methods makes it easier to handle rotating geometry. So wind turbines, of course, are rotating geometry. And then we use Nalu Wind as our near body solver. Yeah, it can handle complicated geometry, anisotropic mesh, mixed elements, and RANS models. And then Amr Wind, which I've been talking about, we put this in the off body and that handles atmospheric boundary layer and wakes. You can also turn on mesh adaptation and track the flow. So Tioga is what does this Oversight mesh connectivity. It's an open source library that anyone could use. And then to get this to work, there were some modifications to the AMReX linear solvers, and these are in AMReX, so anyone can use this, but you can specify internal Dirichlet boundary conditions to the domain. And that's necessary when you pass the solution across from both the solvers. You have to enforce some boundary conditions. The way we pulled this off, we just loosely couple at each time step. And so at each time step, they pass the solution and they independently solve things, and then they pass it back, and then you move on to the next time step. And I'll note here that the way we've set this up creates some pretty interesting load balancing problems. I'll kind of describe this, but I think John has more to say about this later. But we run all this through, we call it the ExaWind driver, but it orchestrates, say you've got a bunch of wind turbines, you could have multiple instances of Nalu Wind. And so you can run many Nalu winds, and then you could have Amr Wind doing the background. And we have support to do full overlapping So you can overlap the MPI ranks, or you can run them exclusively. And also, in addition, you can run in a mixed mode where you run some on CPUs and others on GPUs. And so there's a lot you can do there to load balance the problem. You can, if you're interested about in really fast time to solution, you might choose exclusive mode, but then you have to be careful about how many degrees of freedom you use on each solver so that they're more balanced. If you're more interested in not worrying too much about how many cells on are in each solver, you can do the overlapping, but that tends to be a little slower because you have to wait for each one. All right, so now I'll show off some of the oversight simulations of wind turbines. These days, we're still relying a lot on just static mesh adaptation. And so typically for an atmospheric boundary layer, we need mesh resolution of about 10 meters. So that's on the outside of the domain. And then where we connect to Nalu wind, we're at about 0.1 meters. That's pretty typical. And then the Nalu wind mesh will go down to Y+1. So let's say microns. So we really have like a really wide range of scales that we're trying to simulate. Here's one of our latest simulations. So this is a hybrid RANS LES simulation. There's 2 wind turbines, and it's in an atmospheric boundary layer. That's pretty exciting. And then we have a movie version of this. We haven't really done too much with dynamic mesh adaptation because in these large eddy simulations, it's kind of hard to know what to tag. It just kind of turns into a mess of vortices. So we've been mostly sticking to static mesh adaptation for now. Let's let that finish. All right, do you want to take over, John, on this slide?
Sure, I'll finish up the slides and mostly talk about things like crusher status. Yeah, I feel like we're only giving everybody probably like 10% of this project because there's a lot more to it. We're going to move to offshore stuff in the future. And honestly, AMR Wind is a little bit vanilla compared to a lot of the rest of the talks here, except for, we're doing wind and water in there with volume of fluid. And I feel like one thing that's really unique to our project is the coupling to Nalu wind that's doing an unstructured solver. So yeah, I'll talk a little bit more about the hybrid turbine simulation status. I don't know, I thought maybe it'd be interesting to kind of give an idea how close I feel we are to meeting our KPP. AMR Wind, since we branched off at InkFlow, we were kind of already set on the path to just easily run on GPUs right at the start of using AMR Wind, so we can run on NVIDIA, AMD, and Intel GPUs pretty easily. We've run the hybrids, like the single turbine case. We've run that a lot on CPUs. We've been super successful in the CPUs. We run that on Summit, on the GPUs in a mixed mode. I've also run the in mixed mode on Crusher. And one thing that's cool about Crusher is we can fit the single turbine case with like 500 million cells on AMR Wind and then run Nalu Wind on the CPUs on a Crusher node. Because Nalu Wind, for an example, Nalu Wind on the blades will do maybe 7 million elements to do the unstructured mesh, and then AMR Wind will do about 400 million cells. So there's like a 400-to-1 disparity in like the codes and the amount of domain they're doing. But we can fit the full single turbine on a single Crusher node, which is kind of cool. What else? Yeah, so one thing that I think is pretty cool about our project that I haven't seen in a whole lot of projects over my career is we can saturate a full node in this case, run Nalu Wind on, spread it across, and we can strong scale Nalu Wind on the CPU pretty well. Nalu Wind is currently, we can run on NVIDIA GPUs in Nalu Wind, but we're still trying to port to AMD. Nalu Wind uses Cocos and all that, but we're still working to port it there. So in the meantime, I've been running Nalu Wind on the CPU and just totally saturating a node. It's pretty cool from a computer science perspective. And I don't know if people are aware of like how you would do this on Summit, but I have to like explicitly place the ranks on Summit, and I'll show you an explicit resource file that I use on Summit, which maybe people aren't super aware of. I thought it might be interesting. And we've also run the single turbine case on Summit on all GPUs. So Nala Wind on the GPUs as well as AMR Wind on the GPUs. Can you move to the next slide? So there's a little matrix that I put together and like kind of the status that we're at. So the single turbine, we're doing pretty good, 2 turbines on the CPUs, but we're ultimately working now to trying to get this 4 turbine run to work. And now it's kind of at this turning point where we have the CPUs, we don't really have a machine that we can run the 4 turbine case on with enough CPUs to do it. So now we're using Summit and trying to really do the turbine simulations on the GPUs. And I still don't fully understand. We're not using a totally MP-MD situation in our code. We have the ExaWin driver, which is a C++. We're just attaching all these libraries to it. And it doesn't really act in the exact same way that when you can run these codes separately. And we're still trying to figure out all that stuff as we go along. So yeah, we're just kind of working on the 4 turbine case, which is like, 20 billion DOFs, 10 billion DOFs in AMR Wind. So it's a pretty big simulation. Can you move to the next slide? So here's an example of how I totally saturate Summit. You can kind of see you just write this file. I have a Python script that writes this file out, and you can see the ranks are numbered, 0 to 5 is the AMR Win ranks that are attached to a GPU. And then all the Nala Win ranks are spread across the rest of the CPU cores that are available on each node. And then you can see it resets as we go to rank 6, 7, 8, 9, 10 on the right side there. And then you have the AMR Win GPU. So I kind of interleave all of the ranks together and utilize the full node. You can go to the next one. So a couple of Crusher results. This is pretty similar to, I work on the Pele project too. It's pretty similar to what I see in Pele for an AMRex code. When you factor in the amount of GPUs or GCDs, I consider a GPU on Crusher to be 1 GCD. So I would say 8 GPUs on a node. So when you kind of factor, like if you matched 6 GCDs to 6 Summit GPUs, I think it would be pretty similar in performance. So this is on a node per node basis on the left plot. We just get a time per time step that's a little bit better on Crusher than Summit, just based on the full node, even though we have more resources on a Crusher node than a Summit node. On the right side, I did a little strong scaling, and one thing it's pretty obvious on a Crusher node is you can fit like a 5 times the size problem. So 5 times the number of cells on a node. So we can fit 500 million AMR Win cells on a Crusher node, which makes our strong scaling look a little bit better because we can fit so many cells on there. And I guess that's probably all I'd say about that. You can see the right side kind of corroborates the left plot too, and that we're a little bit faster on Crusher than Summit, so we're fine with that. We think that's good. Crusher, it still seems to be pretty early on. We run on Articus too. I run on it. We can't say anything about it. It's not that interesting. We can move on.
Do you want me to do this slide, or do you want to do this?
Sure, yeah, I can just jump in if you have anything else to say, but you can finish.
Okay. All right, so just a quick conclusion. We showed some strong scaling performance and some small improvements. We have validation on atmospheric boundary layer problems. We showed some hybrid solver results, including blade resolve simulation of a realistic wind turbine, I guess 2 turbines we showed. And we're fully ported to GPUs and run on Summit, Arcticus, Perlmutter, and Crusher.
I'll jump in and just say one extra thing about Perlmutter that maybe is interesting to other people. Is we just see about a 20% speed up from a V100 to an A100 and AMR Wind, if anybody's interested in that. We get a speed up, but it's 20% or so.
Right, and then final slide. So some future work, always improve scaling and performance. It'd be nice to get the hybrid solver completely on GPUs, even though there's a chance we may not run it that way, but just having that ability would be nice. Focus more on offshore wind energy, so get our immersed boundary or EB capability. ready to go for those kind of simulations, multi-phase flow, and then whether or not we're going to use actuator lines or the hybrid solver for offshore, or maybe both at the same time. We hinted that there's some interesting load balancing, so we want to investigate that more and see where we can go with that. And then turn on dynamic mesh adaptation. And the figure on the right, we turned this on for, we had this ellipsoid problem that we run, kind of like a fake one-bladed wind turbine, but though it does work, we just haven't really pushed it too much in that direction yet. So it'd be nice to put more effort into that. John, do you want to talk about the ZFP?
Yeah, I feel like that's my thing. I know it's like possible, but I've really been trying to get ZFP to work in plot files. I added HDF5 support to AMR Wind. I really just think it'd be a cool gap to fill between, to have it working between in situ visualization and then just uncompressed plots. Because I'll give you an example is now we're at the point where we're doing this 4 turbine simulation and a single plot file from AMR Wind is 1 terabyte. And I've always heard things from ZFP of like 101 compression ratio and stuff. So I was hoping to get that. And I've done a bunch of examples but I just can't view them in Visit. I've always heard that if you have ZFP and HDF5, it should work, but I could never view it. So I'm hoping to get that to work sometime to mess with that. And then also, since, we have these huge plot files now, we're just at this turning point where obviously we need like in situ visualization. So I'm really hoping to start to use Ascent as just like kind of an always on thing in both of my AMRX projects really at this point, because we're starting to do such big runs now that I'm kind of excited to start to use that. And we just haven't used it that much. We've had people who've used it and implemented it in our code, so that it works as far as I know. But in general, like the people who develop and work on the codes aren't using the in situ stuff quite yet. So I'm hoping to do that in the future.
All right, I think that's it. Any questions? I'll put it back on the movie.
Yeah, thank you, Mike and John. Any questions?
One, Mike, you showed one of those scaling plots earlier on, sort of mid-talk, where there was, I don't know how to describe it, but there was a couple of dots next to each other, then it would drop down a little and have a couple next to each other. Do you know what I'm talking about?
This one?
Yeah, the triangles. Any idea what's up with that?
Yeah, this is just a load balancing thing. It probably cut the domain up into the same number of blocks, let's call them. So then when you added more nodes, it didn't really help.
Similar to what's happening in the circles down below it, you think?
Yeah. Yeah, exactly.
All right. That's it. Thanks.
Axel wants to know about the dune worm.
Yeah, it's slide 18. No, the one after 19. Sorry, didn't keep proper track. Yeah.
Oh.
So you said like this is, I didn't understand it. Is this like a trace line of the field or is this something else?
It's either vorticity or Q criterion. So an isosurface of that. So yeah,
Okay,
there's a we call it an ellipsoid, but it's just kind of like a flattened long ellipsoid. So it kind of looks like a turbine blade, but without a blade like.
Oh, the turbine blade is not shown, and okay, yeah.
Yeah, but that would be, I don't know if you can see my mouse, but on the left side of the domain. So then the flow comes in, and while it's spinning, it creates these vertical structures, kind of like you can see them in the wind turbine here. So it's kind of the same. You get 3 of them, and you've got 3 blades. And then when you've got 1 blade, you get one on the inside and the outside.
Cool.
So the turbine, you don't really, the inside ones are very small because the hub does something to those. But if there were gaps, you could see like an inside vortex too. It's kind of cool. Yeah.
Nice. Is this like a standard thing that you visualize and analyze because it like affects the next turbine if there's too much vorticity still, or?
Yeah, so I
What's the
kind of
science
hinted to
behind
that. So this just had uniform flow. So it's pretty easy to find a Q criterion or vorticity and make an isosurface, and it looks pretty. But as soon as you do that for one of these, it's harder to tell. But what you said is correct. You know, the wakes hit each other, and then you get less power from the downstream turbines. And so yeah, that's pretty much it.
Cool, thanks.
I guess if you looked at velocity, yeah, like a slice of velocity, you could see maybe a wake deficit. That'd be another way to kind of visualize the wake. The Q vorticity and Q criterion, I think, yeah, because it's all mixed up, it's a little harder to tell sometimes, especially if we'll get more turbines in there. It'll just be a vortex soup.
Just curious, not to beat a dead horse, what's the color here? Why is it red on top and blue on the bottom?
Huh, that's a question for Nicholas. I think Nicholas made this.
Okay, I can look at it.
Yeah, I'm not sure. I'd be guessing. I'm wondering if it's sometimes isosurfaces of velocity magnitude kind of look similar. Or maybe one's like a positive vorticity and one's a negative. I'm not sure.
The ABLs are always like red on top.
Oh, you mean this red and blue? Or
is that what you mean?
The vortices shed from the right, the vortical structures all tend to be red on the top, but I wonder if that's not just like the mean flow velocity and kind of parallel to the ground.
I feel like it's part of the ABL. Like the ABL has a gradient to it, and it's just, you can see the bottom of those wakes are all blue, and then the top of them are all red. I think it's just part of, like, if that's the temperature profile or whatever it is.
Oh, okay.
Yeah, we'd have to ask Nicholas. He generated this.
I have a curiosity, maybe a stupid question. The turbines motion is imposed, or is like they move under the forces due to direction with the wind?
For these simulations, we just enforce a fixed rate. So they just spin about a point. But we also have links to OpenFast. And OpenFast can do all of the modeling for the like beam bending, and there's controllers in there. So eventually it'll feed back and forth. And so you'll kick it off, and then the controller will tell it to speed up or slow down.
Yeah,
I
there's
didn't
a
really
lot
mention
more.
the OpenFast connection.
Yeah, there's a lot more to this project. In Nalu Wind, OpenFast is coupled to do the fluid structure interaction. So the blades can bend back. The blades can deform on this, and they do the pitch and the yaw or whatever on the blades too. So there's a lot of like little intricate geometry that's going on the turbines.
Thanks.
Mm-hmm. And OpenFast is an open source project too. You can probably find that pretty easy on Google.
Yeah, that's what controls the turbine itself.
I want to ask another question if I can. John, can you say at least a few words about how you manage the running the code actually on the CPUs and GPUs at the same time? What does the code controlling structure look like to do that?
It's pretty easy, actually. I mean, so we don't use npmd. We're not running two applications just at the same time. We have a driver that you compile the code just like a standard, like we include sundials into Pele C or something. The driver compiles in and links to Amr Wind, and it links to Nalu Wind. And when we run it, we basically decide whether or not we want to overlap Nalu Wind on the same rank as the Amr Wind ranks, or we can separate them and run them explicitly. So we can have basically all the set of Amr Wind ranks on the left side of the COM world and all of the Nalu Wind ranks on the right side. And if you just run that in JSRun or Slurm or something, you would basically just have everything for Amr Wind on the left side and everything for Nalu Wind on the right side. So that's why I showed those explicit resource files in the way that I actually take every single rank in the world and I place it exactly where I want it on the system. And on Summit, I actually even like on the cores that are closest to the GPUs or whatever, I place all the AMR Win ranks there that are associated with one GPU. And Nollywind takes all the rest of the ranks on that node. And that's how we fully pack a node on Summit. Slurm, it's not so easy. We don't have like an explicit way to do that as far as I know. So I don't really know how to do the mixed mode there. But when we run Nollywind on the GPU, it's pretty straightforward because we just put one rank per GPU like we always do in the codes. So if we're running it both codes on the GPU, it's pretty easy to do that mapping, if that explains it.
Yeah, thanks.
Yeah, our executable is just called excellent. We just run excellent and then it does.
I had a question about the Zfp compression that you're doing.
Sure, I'd love to tell you.
Are you using the HDF5 writer that's like part of AMReX now that Hojun Tang added?
Yeah, and the way that I was testing this was, well, first of all, we use CMake and AMR Win, so that's not, I was gonna make a pull request to put that into CMake in AMReX. So I just did the GNU make like tutorial thing in AMReX to try to see if I could visualize just a ZFP plot. And I can get it to output the plot and I can see that it's smaller than a regular HDF5 uncompressed plot. But when I open it in Visit, even the newest Visit, I can't view it. But to really answer your question, in AMR Win, we're using the standard way to write plot files.
Okay, yeah, so yeah, so that would be much appreciated if you could make a pull request adding CMake support for that.
I plan to do that, yeah.
So are you in touch with Hojun? Because I think he has been visualizing the compressed files.
Okay, well, that'd be great. Yeah, I would definitely love to.
All right, so I'll send out an email putting the two of you in touch because I think it should be doable. He was doing it somehow anyway.
Okay.
Let me make a note of that.
Awesome, thanks. Yeah, we have this 1 terabyte plot file and it broke ParaView. I had to send it to Kitware so they could find out where it was breaking ParaView.
Okay, so I'm going to take the position that we're now discussing. So this is the discussion part of the session. I guess one thing, one thing I wanted to collect was if there are any like glaring performance issues from the AMReX side that are sort of inhibiting your ability to make your KPP goals. And it kind of sounds like the answer to that is no right now. And if that's not correct, you should correct me. However, there was this thing in Mark's talk, and I think you said that this wasn't like a showstopper, but there was a big bottleneck in the parallel copy.
Yeah, I would reiterate that on AMR Win too. I think in both of my projects, that's always at the top of the profile in anything we're doing.
So I'm wondering if I know that on the particle redistribute benchmark, I've tried running just that operation by itself on up to all of Summit, and I don't see any kind of like spike when you go to a large number of nodes. I'm wondering if we should do the same thing, but for just the parallel copy operation and see if we can like isolate that. Do you have any comments on that? I don't know if Wei Chen is on
the
call. Yeah, he is.
So I'm just wondering, is it possible it's because of a load imbalance? The problem of
in Pele C, we definitely see that when there's a load imbalance that it exacerbates the parallel copy. But in AMR Wind, we're using static refinement and all the cells are pretty much doing the same amount of work. So in that case, I don't think there's a load imbalance issue and we still see, but AMR Wind doesn't do, in my opinion, a whole lot of computation per cell. A lot more communication based on the linear solves.
Yeah, it might be the linear solver has to call a lot of parallel copy because of what we do is kind of like aggregate all the grids together. So in the beginning, you might use say 1,000 node, and at the bottom, maybe only we collect all the data to just like one processor. So during that process, you have to do a lot of parallel copy.
Yeah, but in Pele C, there's no solver.
Yeah, for Pele C, it has chemistry, so I suspect that the load balance might be the main issue.
Yeah, we definitely have to look into the load balancing more in Pele C, because we haven't done that yet. So I think that's definitely part of it in Pele C.
Because a lot of time I see is that when the field boundary or parallel copy or those kind of things shows up, is actually because of the load balance issue. Because even though it's a point-to-point communication, but the process doesn't have any work to do before the parallel copy, it's just sitting in the parallel copy finish. If you need to receive a message or need to send a message, it just sit there. So it appears to be much longer.
Well, it seems like an excellent, obvious suggestion to make a standalone test for that copy stuff and verify that it either is or isn't sort of inherent to the operation. We should have done that by now. We haven't. We need to do that.
All you could do is just manually modify the AMReX source code where the parallel copy happens. We have a profiler, BL prof thing. Immediately before the BL prof, you can insert a parallel descriptor barrier, so that the profiler only measures time that after every process has reached that point. So maybe we should make that a runtime option, so that make it easy to.
I seem to recall Paul Maloney looked at this a little bit in the context of AMR Wind, and I feel like he was caching computations or something, and he got a little bit of speed up. And I don't really remember much else. But I don't think he ever made any pull request for it or something, because I think it was fairly invasive in what he did.
Yeah, I couldn't remember. Yeah.
I'm kind of making that. Oh, sorry, go ahead.
I was just gonna say, but that's that issue. I mean, we don't have to like dwell on it.
Yeah, I'm making a list of kind of action items about that. So I think one is just investigate the scaling on a perfectly load balanced, a problem we know is perfectly load balanced in isolation. And then another action item is maybe to add that runtime option that inserts a barrier before the parallel copy, because I think this comes up a lot. We're always trying to figure out if what we're seeing is actual communication cost or a load imbalance. So I agree that would be useful. Possibly another topic for discussion. So I know, so Axel is working on Python bindings for AMReX for the WarpX project. And I know that AMR Wind folks use that in some capacity, or?
So we have this ExoWind driver application, and it started out as a Python thing. So we could couple both of our codes, Naluwind and AMR Wind, through. It was launched through Python, so we used that to begin with. But we wound up moving to a full C++ driver, so we kind of don't use it anymore, but we have in the past.
I see.
Yeah. So you had an implementation on Thyssen, I think. That's like a language on its own. It's like a mix of C and C and Python. Actually, it would also be a question, because I know that you have a relatively large software stack, what you use to deploy that, but there was another question that I had for you. But the answer, or maybe staying on topic for a sec, what we do different than previous implementations for PyAmReX, so there are at least two that already existed and were used like for ExaWind and for another application, is that this time we can actually use it with arbitrary compilers probably quite easily. Because we do a native C++ header-only library implementation. And so with that, I'm quite confident that we include also the whole data exchange stuff for also Intel GPUs and TIP. And generally, I think before even CUDA GPU Exchange was not even in that, because it was before used mainly for driving applications and doing setups and so on. So that's the new angle to that is really that we are fully GPU aware for hopefully all three big vendors. We start with CUDA currently and add the other protocols later.
Yeah.
Yeah, the question. So one of the drivers that's for us maybe relevant for that one is that we really want to have more complexity to manipulating our simulation, where a lot of people want to script and control the simulation in a sense of adding another kernel without writing it in C++, or maybe writing analysis. If that's something of interest also to others, yeah, please feel free to reach out. We have a channel also on Slack that we can discuss the progress there. I'm currently adding this thing that we need to drive our simulations. But it's very easy to add more methods and add more classes that are your favorites, Amrex.
Oh yeah, that reminds me, I've said this in the morning session, but if anyone wants to be added to our Slack workspace, please send me a message using the Who the Thing, Andrew Myers, and give me your email and I'll be happy to add you. And yeah, Axel's leading the effort on the Pi AMRex stuff. So if you're interested in using it or would like to help out, he's the one to talk to. So another thing that, Mark Henry, I don't know if he's still on here, but we were talking about potential places to use this multi-fab version of Parallel 4. And he was pointing out that he doesn't think it's currently being used in all the versions of redistribution that are in AMReX Hydro.
Yeah, I don't think Mark's on anymore, but I can maybe speak to that a little bit since I work with Mark a lot.
Okay.
But yeah, I mean, we've just started to, so I feel like it's fully implemented in AMR Wind, but we use AMReX Hydro for mol there, I think. But in Pele C, we use the state redistribution. And I think it's just the case that we've started to port our simple MF-iter loops to that case. There's a lot of MF-iter loops that we have in Pele C that are huge that we can't port. But yeah, I think he just noticed that in AMReX Hydro, maybe that hasn't been converted yet. I think that's what he was hinting at. So I don't really know. I haven't looked into it very much.
The AMReX Hydro acts on a fab basis. So the switch from regular MF-iter to multi-arrays MF-iters should be done in C or LM or LMX. But then the question is whether or not it's compatible, whatever the operation done within the AMReX Hydro, I guess.
I'm not familiar with the AMReX Hydros, those functions. So are those functions you call from Pele? Are they like a host function or device function?
Host.
Okay. If it's a host function, then the interface has to be modified for that to work. If it's a device function, then probably we don't need to change anything. Right. So I mean, is that right? Yeah. So suppose like because right now, I assume in like say Pele, you start the MF-iter loop, then inside you call host function in AMReX Hydro.
Yeah, you're right.
But now, if you start a Parallel 4 that the multi-fab Parallel 4, then you don't really actually have a host function call anymore once you're in, right? What you provide is a device function to the Parallel 4. So that device function is taking like 4 arguments. What's the box number and what's the cell index IJK. So
no, you're right. Good mixed up.
But before we do that, there are still a lot of so we have to extend the EB support for the MF Parallel 4 stuff. I don't think the Parallel 4 function need to be modified, but we need to what we have to do is so we have this EB factory stuff, right? So right now, what we typically do is before you call start your MF feeder loop, you use the EB factory to get the EB data you want, like a volume fraction, area fraction, right? Those are kind of like a multi-fab type of data. So then inside the MF feeder loop, you can use the MF either to get the like a fab for that volume fraction or area fraction stuff. But we have to provide the support for like the EB factory need to return a new data structure, and that new data structure can be lambda captured onto device. And once you're on device, then you just kind of use similar thing like what we introduced, what do you call multi-array forcing, right? So you have those type of things. So then given you can probably have, we don't have that yet, but you can write those things. That thing can have a function called a volume fraction, will give us the volume fraction for that fab. I guess what I'm saying is that there are a little bit of work we need to do to add the EB support.
Do you feel like it is fairly complicated or something that I can just relay it to Mark since he's not on, if it's really possible or not?
I don't think it's that hard to do. Yeah, I can probably do that if, yeah, in a couple of days.
Okay.
So I think my plan, if I want to do this, I'm probably going to do that to, I can use this linear solver things in Amrx to see if we see a good, benefit from that. Because currently our linear solver stuff, all the regular thing, we're all using the the multi-fab version of Parallel 4. But for the EB stuff, we're still doing it for each individual fab. So we can start from there, and if that works well, can try to extend that to, AMRx Hydro.
While we're on the EB topic, we did do a certain optimization to the state redistribution in AMRx Hydro that I haven't made a pull request for yet, but there was a pretty large private thread arrays in the state redistribution that we solved, but I didn't really solve it in the best way. So I'm trying to debate on how I want to do a PR for it. But in certain cases, we've seen the state redistribution be about 10% of our runtime in cases where we didn't have a lot of chemistry in Pele C. So I did notice that there was a way to speed that up. But I just thought I would mention it that we have something that speeds it up by like 4% or so.
Yeah. So yeah, I like to see what modification you did to improve it. Yeah.
But I don't want to monopolize any discussion if we're talking about Pele so much.
So I guess another thing that we mentioned in the AMReX presentation that's relatively new is support for the STL geometries. Well, it's not new for Pele as I understand it, but it's new that it's part of AMReX and that other codes can use it in general. So I think the WarpX people are interested in using that. Is anyone else? My understanding is that for Infix Exa, the sort of additive geometry is sufficient for like their challenge problem.
We have the ability to specify geometry through a CSG file.
Okay, is that also kind of it's based on implicit functions, but that can build up to be quite complicated?
Yeah, you use a graphical kind of interface to construct a geometry, and it saves it as an ASCII file, and then it's interpreted at runtime and converted to an implicit function and handed off to AMReX.
Okay, cool.
So Andrew, the way you asked the question was a little weird. You said, do you need it for the KPP challenge problems? The answer is probably not, but would it be useful moving forward? Almost certainly. You know, as we start to look at a number of different applications to try to use these codes, and the geometries can kind of get arbitrarily complicated, and we may only have the geometry as a surface file.
So Jordan has a good argument of why STL is not a good choice compared to CSG. So maybe Jordan can tell us.
I think Wei Chin just threw me under the bus.
No, I was convinced by you, because I saw the issue, you mentioned.
Yeah, so the kind of the previous iteration of our code, which we call classic now, it uses STL files for specifying complex geometries in the code. Several of the issues we've run across, one is if your faceting of your surface is too coarse, you end up with kind of an odd tessellation that shows up in your simulation after the fact. And the only way to get rid of that is then to really mesh it terribly fine to some degree, where your mesh is going to be at or below your grid spacing to some degree. And in which case it sometimes leads the ability to generate the geometry a lot more problematic, and that you can, have, tens or hundreds of intersections between facets and grid cells. And it just seems to be really complicated. That's why we kind of shied away from that and stuck with this approach of using somewhat implicit functions still as we go to this like CSG based format.
Yeah, I think ultimately, if you really had a distance function for whatever your geometry was, you knew that it was smooth. Yeah, the problem is, or the advantage to the CSG is you sort of have an idea of what happens between the grid points, right? In a sense. Whereas once you have a triangulated surface, if they're all triangles, then they're going to be planes. And so you're just, if your shape is complicated and you have to define it by a bunch of triangular facets, there's just no way around adding more points, right? But I mean, I guess there's things like NURBS and other higher order surfaces. But yeah, you thought the triangulated surface stuff gets complicated. I can imagine doing the distance functions or intersections with NURBS or higher order things, but that's got to be hideous.
Yeah, we've had issues with water tightness as well, or you start merging facets together or edges together nodes. So yeah, we've run into just about every, and that's why we kind of shied away from that when we had this kind of, since AMRex takes an implicit function, the ability to generate one on the fly. We try to exploit that as best as possible anyway.
Yeah, and one of the first versions of the surface stuff that we did was taking a triangulated surface and make a distance function out of it, so that we can just sort of plug it in in kind of the same way you talked about. But I think that this kind of faceting problem reared its ugly head when you started to do complicated stuff. And I think that's just a known problem anytime anyone does either CAD or CFD with complicated geometries. And it's just, at some point, geometry just becomes hard. I guess a corollary to that is when you recognize that 99% of your geometries can be made up by adding together very simple shapes, then you need to take advantage of that. That's what you did.
Yeah, and then really we work with chemical reactors, which if you see them in real life, they are literally just a bunch of cylinders or squares that have been welded together. So we do have that kind of advantage.
Yeah, I should show you what some of these combustors look like. They're interesting, put it that way.
Okay, well, I guess the capability is that the STL capability, I guess the takeaway is that the STL capability exists. And is there people want to try to use it?
The CSG stuff sits out there as well. If anybody wants to use it, they can reach out to us. It sits out on, it's on Infix's GitLab, but it sets publicly. So you just need to tie it into your code and build against it.
Cool. The only other thing that jumped out to me during the presentations was that there's three of the codes that are doing reaction networks, Nix, Castro, and Pele. And it's not clear to me how, it kind of seems like to a certain extent, three codes are doing three different things. And this is frankly not an area that I've worked much in. So maybe they're doing 3 different things for a very good reason. But I'm wondering if it could benefit from more collaboration there.
So we have a bi-weekly meeting with the Sundials folks that involves Gene for Nix and some of the Pele folks. And we do try to sort of search for commonality, at least between those 2 applications, and have done fairly well with that, I guess. It is true that the Castro effort is doesn't join in on that, and maybe there could be a benefit from another voice there. But I think we're working that as best we can. I mean, that's where we sort of learn the difference. There's some fundamental differences between what Gene is trying to do with Nix and what we're trying to do with Pele, but there's also a lot of commonality as well. And then the other thing to say is, there is this effort at Berkeley there to have sundials actually drive the time integration loop. And the temptation would be to throw that in with the same stuff, but I think that that's different enough that maybe there's not a whole lot of commonality there. But maybe David can make a comment about that. I don't know.
Yeah, I'd say it's maybe early to leverage that sort of thing in Pele or Nix yet, but perhaps someday.
Okay, I think that's about all I wrote down to talk about. Does anyone have anything else they want to bring up? I think we have about 5 minutes left in the session.
I'm curious to ask you or Ann or John or Wei Chen or whoever, what are some of the higher priority things that AMReX is working on that haven't been brought up in this context yet? Where are you putting some of your efforts at?
I think something right now, I think a thing in general we're interested in is having better support for doing mixed or reduced precision calculations. For example, I know there's a thing in the particles where, so the particles are a bit limited in that you can either use 3 floats to represent the positions, or you can use 3 doubles to represent the position. There's things that store kind of like an integer plus like a offset kind of thing that might work better. So we want to generalize that data structure somewhat to allow for that. And I think there's also some stuff on the linear solver space that we think would benefit from mixed precision. I think Axel's raising his hand.
And it's maybe a quick announcement exactly in this direction. So we want to explore this actually this summer with an intern to generalize the AOS exactly for that reason, to be able to express this as an array and also be able to have additional coarse and fine positions. Because we have the problem that if you have either a large simulation box or moving the particle position far way out, then we're losing precision and then we can't use single precision anymore. So that's exactly our challenge for the position and for field gathering. So if that's, but that one would be a thing that potentially, we probably just have to add a new method and interface for that, but potentially everyone would have to maybe update slightly. We'll try to make this compatible, but we'll see how this goes. So that would be one change that we want to really push through. We saw this recently again, also when we ported for Fugaku and we had like someone optimizing vectorization. The first thing they did is like declutter that one area of struct and make it also an array. So it's, that would be really useful for us generally.
Wei Chen, do you want to say anything about mixed precision on the solver front?
Oh, so what we have tried so far is so in a multigrade solver, so on the original level, we solve in still the original double precision, and then at the coarse level, we solve in single precision. And it turns out it does not hurt the number of iterations. It takes almost exact number of iterations. So that's good news. But the bad news is that, at least for the tests I have done, is that the most expensive part is actually the smoothing because it's a single GPU test. It's actually the smoothing on the original level. So which means we have to move also the original level to the single precision. So we are exploring that. So so we have a new person, Dean, is working on that, and Hanji is also working on that. So that's my, yeah. And the thing is, we also haven't, oh yeah, I tried the probably up to like 64 nodes, that type of a thing, because the idea is it also it might reduce the communication time, right? But up to like 64 nodes, I haven't seen big difference. One possibility is for the linear solver, a lot of our communication is still like our linear solver has like a single ghost cell, sorry, yeah, ghost cell, right? That's typically what we have because we don't know high orders thing. So the amount of data you need to communicate is actually not that much. So maybe cut it down by half doesn't save you too much, because maybe it's still dominated by latency, not the the bandwidth. So, but we don't know. Maybe you go to a more node that might help, might change.
So just wondering on that, Wei-Chin, you mentioned earlier that when, like in the linear solve, the parallel copy, when you do the aggregation and so on, is taking a lot. If you do all of that in single precision or instead of double, that's still, I mean, that sounds like a.
That's right. That yeah, that could move a lot of, have to move a lot of data that could help. So yeah, so that might, that's what I mentioned. I only, the tests I've done is only kind of small tests. So maybe on big tests that will help.
Okay, yeah.
And yeah, so.
All right, I think we're at the end of our time. So just I want to thank everyone who spoke for some interesting talks and for a nice discussion. And again, if you want to be added to the Slack channel.
Okay, I say one last thing. I just remember this. So I've been pondering this for quite some time. So I think we should move to that direction. So it might actually break your code. So, but if it breaks your code, it should also be easy to fix. What I'm talking about is, so since day one, we have been using the CUDA Nord stream, the legacy stream. But I think we'll have to move away from CUDA Nord stream. So what's currently happening is if you do something inside the MFT loop, it's actually using non-Nord stream. So that's fine. But if you're outside the MFT loop, if you just call some parallel for function or call some AMReX function, it always use Nord stream. I think the potential issue of using Nord stream is it may not work well with the like GPU aware communication. So because we call an MPI function, MPI is going to do some work to move the data. Now suppose we give them the GPU memory thing. So it might involve the GPU work. So it may involve some CUDA API. They have to call some CUDA functions. And we are also calling CUDA function on our side. And if it's Nord stream, it will force a lot of synchronization. So that's a potential issue. So, but the thing is, if we move away from the Nord stream, it could be some code, you to work because it depends on that Nord stream behavior. Now suddenly might break, but I think it should be easy to fix. So just a heads up.
Okay. All right. Thanks. Anything else to talk about right now? All right. Well, thank you, everyone. Thanks for a nice session.
Thanks for putting this together, Andrew. Appreciate it.
Sure, thanks for speaking. Paul, do I need to do anything special about the recording?
No, I'm just going to push the stop recording button right now. I'm doing it actually right now.